All right, let's see if this works. All right, good afternoon. I appreciate the opportunity of having me here again at NANOG. The topic this time is optics still, as usual, but it's going to be around 400G, giving you a bit of a market view. Finisar, for those of you that are not familiar with it, we're the largest manufacturer and supplier of optical transceivers into the industry, mainly OEMs, but also end customers, networks, users, data centers. So let's talk about, again, 400G and how the deployment models and the deployment trends are happening in the industry. And I'm going to take a look not only at the hyperscale segment of the market, which is, of course, where the leading edge is and what's driving deployments early on. I'm going to touch a bit of that, but also some of the implications for deployments after that, like smaller clouds and also enterprise eventually. So within data center racks, just to set the stage, right? We know that 10G has been deployed for a long time. 25G Ethernet is being deployed now, mainly in the hyperscale world. And the assumption is that then 100G or 50G will follow, probably a combination of both, depending on who you talk to. But we need to start getting ready for 100G to the server. If we look at connections between data center racks, 40G is still being deployed. 100G is the majority of being deployed today in those large hyperscale networks in data centers, with 400G being next in that space. But as we will see, there's still a lot of 100G that will be deployed for a very long time. And then, of course, between data centers, longer spans, DCIs, that was traditionally the space for 10G DWDM tunable modules. That's now giving way to coherent optics. We're going to touch a bit on that as well, coherent 100G, 200G. And then, what are we doing to get ready for 400G and beyond between data centers? So if you look at a bit of a market data, right? This is a market data slide from Deloro, and these are actually port shipments, Ethernet port shipments in millions. And as you can see, there's still a lot of volume for 100G and 200G. The 200G number there includes high density 100G, is 2 by 100. It also includes native 200G Ethernet, although that's still a question mark of how much of a market that will be. But some of us believe that in the enterprise space, 200G will be a very interesting cost point overall. And as you can see, 400G is shown there at the top in gray. So if we zoom in after 2020 into that 400G segment, we see that obviously early on, it is really the large cloud service providers, the top 4 in North America, the rest of cloud following in the green bars, with enterprise starting to appear there in 2021 and beyond. So it's a lot of debate of how quickly this ramp will happen. This is Deloro's view. It may happen in this manner or a bit slower, but it's certainly starting to happen, I would say, next year in some of those major hyperscale data centers. So what we're discussing here is the transition from a model of a 32-port switch, Ethernet switch, using QSFP28 100G to in the hyperscale case, 32 ports now 400G, with all the implications in physical form factors and thermal dissipation and optics, of course, that we're going to discuss, moving from a 3.2 terabit switch to a 12.8 terabit switch. 200G model, 6.4 terabit is shown there in the middle. As I said, there are some that are considering deploying that or planning. It could also be an interesting cost point in certain markets. Maybe not in 32 ports, but certainly with some kind of oversubscription for the enterprise space, again, operating at 200G. So don't discount that yet. It really depends how quickly 400G in general comes down in price. If we look at the standardization work to support all these interfaces, and we're going to look at how those interfaces will be deployed in some of these models, we see that the IEEE and as well as the market in general, MSAs, have been quite active on this regard. The IEEE, almost a year ago already finalized the work in 802.3bs, which is the first 400 gigabit Ethernet standard, which is shown there at the top, in the top table. It includes primarily single mode applications, as you can see. There's a parallel walk on DR4, and we're going to discuss that in more detail, as well as LR8 and FR8, which are really like the LR4 equivalents or CWDM4 equivalents in 100G. But now at 400G, primarily for duplex single-mode connectivity in places like carriers or internet exchanges, obviously. What follows in the second table is really next generation 100G to support connectivity to these 400G ports. So these 100G interfaces in the second table, now instead of having 4 wavelengths running at 25G, they focus on 1 wavelength running at 1310 at 100G PAM4, or 2 wavelengths, or 2 streams rather, running at 50G PAM4 in the case of SR2. And then lastly, in the third one at the IEEE, there is now work being done on the multimode space. Multimode is expected to have a longer-term, interesting price points for enterprise, but in the interim, there is these parallel in combination with BiDi technology that are being standardized for certain applications in cloud, hyperscale clouds in China. They're the ones driving those developments, again, due to cost primarily, where multimode can be deployed at a more attractive cost point. The table at the bottom is an MSA. 100G Lambda is the first MSA that has been working on for a while now in some of the gaps that are not standardized by IEEE. So a 2-kilometer 4x100G, as well as some of the longer reach, single wavelength 100G interfaces for certain, again, hyperscale applications. Again, not to discuss this in detail, I'm going to discuss, show you a little bit where they fit on the network in our view in the next couple of slides. In general, technology-wise, it's still expected that anything under 100 meters will still be VCSEL-based, multimode based on VCSEL technology, and I'm going to explain why. And then silicon photonics in the 1 to 2 kilometer space, maybe 500 meters to 2 kilometer space, certainly optimized for 500 meters to 1 kilometer. And then traditional DML, EML, which means DFBs and so on, used today at 100G, will continue to be used up to 40 kilometers at least. Coherent comes after that, and we'll again discuss it again at the end. So the new thing about this, and many of you know this already, the industry is going away from NRZ, going away from ones and zeros in the optical signaling and going to PAM4, which means 4-level signaling. This means that for us, we need to design not only new optics and new manufacturing infrastructure and testing that can support this multi-level or 4-level encoding in the signal, but also for users, right, such as yourselves. You need to know how to install it, how to test it, how to make sure that you get the signal-to-noise ratio and so on. And obviously, the reason to go to PAM4 is to get bandwidth efficiency. You get 2 bits per symbol. And of course, the trade-off is noise, right? So it's harder to build, harder to, shorter link budgets, and so that's something that, as an industry, we need to be aware of. We also believe that SWDM is something I'm not going to discuss here today, but this is multiple wavelengths for multimode applications, will play a role in 400G as well. It is not, however, part of the standard today because it's primarily an enterprise value proposition, and that's not something that the IEEE is focusing on today, as we said. So let's look at some of the form factors that are starting to appear for 400G transceivers. One of them is CFP8 that has been around or being designed for a while. It's in production. You can expect to see these kinds of modules in certain core routers, such as, just like you saw CFP, CFP2 early on at 100G 8 years ago, 9 years ago, you're going to see CFP8 in some of those routers, basically due to time to market reasons. These modules have been under development for the last couple of years, and they're kind of like a CFP2. They're slightly shorter than a CFP2, but they look pretty much like a CFP2, but it's 400G instead of 100G. The one that's catching, of course, the industry attention are the smaller form factors, the equivalent to a QSFP that will now operate at 400G. So there are 2 MSAs in the industry. Many of us are members of both. One is QSFP DD, and the other one is OSFP. And they both have proponents or detractors. And myself and my company tends to be neutral. We build whatever the market wants. And it is true that there are numerous advantages for QSFP DD. It is a module that is backwards compatible. The host is backwards compatible to QSFP. So if the switch has a QSFP DD host, it can accept QSFP 28 100G, or even QSFP 56 200G in the same host. So that provides flexibility at the switch level. It is, however, smaller form factor, harder to cool, signal integrity concerns. So this is all work that's being done by the industry, and we know we believe it will be solved, but it just takes, it adds a little bit more risk to developments and deployments of both the optics and also the switches with QSFP-DD. OSFP is a bigger module, and is actually, the advantages there is thermal management, presumably is easier. The quality of the connector, signal integrity-wise, is better. It's a new connector. It also supports 32 ports, but again, it's not backwards compatible with QSFP28. There are some people working on adapters and so on, but that's actually operationally a little bit more complex, although it's certainly doable. We believe both transceivers in the market will be available. We, as well as many others, are certainly planning for both. There'll be a period of transition, we believe, where both will be offered by the various system OEMs. So there's going to be some complexity, and the complexity will be that depending on who the end customer is, some of the optical interfaces may be available on one and not on the other, right? So early on, it might be that if you want certain interfaces, you may have to go to one or the other form factor, and that's certainly complex as a user and also as a system OEM. But that will, get solved eventually due to market forces. If I have to bet myself, I think QSFP-DD will win, but that's just my own personal opinion. If any of you, by the way, wants to see mechanicals, I have them actually with me. They're very small. So if you are curious and want to see QSFP28 or DD rather, or OSFP, come see me after, and I can show them to you, some mechanical samples. If we then try to map all these interfaces in the media types, multi-mode on the first row, single mode, and then parallel optics with MPO connectors, and then duplex with LC, we can do something similar to this at 100G. I've done this in the past. Now this is for 400G, regardless of form factor. And as you can see, parallel multi-mode, SR8 and SR4.2, again, driven mainly by some of the Chinese hyperscale applications. There's only a DR4, which is mainly the first one that we think will be deployed. And this is equivalent to PSM4, but runs at 4x100G. Can also be fanned out to 4x100. So that's one of the use cases for these DR4 modules. And then a larger number of duplex single mode, as usually happens at 100G. So we have FR8, LR8, which are IEEE compliant. There are a few MSA codes, FR4 and LR4, and then some longer reach codes, ER8 and ZR, which I will discuss at the end, and that's actually now being worked on by IEEE. So if you look at a similar table for 100G, the IEEE standards were actually fewer, were actually 2 or 3 only. The majority were MSA, so there was a big confusion in the market for a while there. At 400G, we're seeing more standardization activity, which is actually good, I think. So the top right quadrant is what I mentioned earlier. That's duplex multimode, not important for hyperscale or for internet exchange or carriers, but it will be important for enterprise eventually. People want to maintain their existing infrastructure, 100, 40, 100, 400. That's, again, TBD as an interface, kind of like an SWDM8, right? But we're many years away from that. There's no market pool at the moment. So how are these things being deployed? It's hard to generalize, of course, on the application or use cases, but this is kind of like a general mapping of how that transition from the 25/100G model today with 3.2 terabit switches to, again, 12.8 terabit switches. They're shown in red. So server to TOR transitioning from 25 gig to 50 and 100, most likely using optics only, copper DACs, which are primarily used at 10G. Still have a place at 25G, but only about 3 meters, right? If we go now to server connections at 50 and 100, that will be a much shorter link, probably not usable. So we're thinking that both active optical cables and multimode optics will play a predominant role in the rack when these interfaces are being deployed. The roadmap now for TOR to Tier 1 or to Leaf most likely would be a combination of DR4, the hyperscale love, that single mode interface. And again, as I said, China is driving SR4.2 and SR8, as well as active optical cables. And then primarily single mode again between Leaf and Spine. Again, similarly to 100G, most likely FR8, which is 2 kilometers, FR4, DR4 as well, for some high radix interconnections between leaf and spine. If we then look at DCI, as I said earlier, 400G is the roadmap next. Could be LR8, ER8 over dark fiber, for example. Certainly the IEEE is now working on 40 kilometers ER8, which is something that's expected to be available relatively soon, actually, as a standard at least. And then ZR coherent for 80 kilometers and beyond, right? Which is, again, also a very interesting application space. And there's work going on in the standards that I will talk about, as I mentioned. So if we now dig a little deeper on the technologies involved in some of these interfaces, right? What are some of the general trends, some of which I mentioned, that are driving those technology choices? So one is, obviously, we said continuous increase in bandwidth density. You notice that we double the speed, we double the bandwidth in the switches, but the actual form factor or the density, port density doesn't change. So the question is starting to pop up now at 400G and beyond. Is the pluggable model good enough, right? At which point pluggable optics will not be feasible, and we will all have to go to onboard optics and get away from the model that we've been used to since 1998, right? 1998 is when the GBIC was introduced into the market by Finisar, IBM at the time, and others, HP. So that's one point. The other point is the increasing adoption of optics, as I mentioned. So larger volume of optics, given that copper now can reach very short distance beyond 25 gig. Low latency optics. Remember that all of these optics, such as 100G, also for PAM4, they require FEC. So there are some applications around cognitive computing networks that might require low latency. So potential optics using NRZ connectivity at 50G, for example, are also possible and are being explored for supercomputing applications today, but they may become more prevalent in non-supercomputing applications. The maturity of key technologies, we mentioned silicon photonics also improving VCSELs to support these higher speeds at 50G PAM4 and 100G PAM4 using a VCSEL for short reach. And then we mentioned coherent many times, right? The driving down the cost and the power and the size of coherent components to support small form factors using coherent technology. So the first one is the form factor, and this is not a surprise to many of you that deal with physical layer stuff, right? So if you look at the module types and the width, right, at 10G, 40G, 100G, even 400G, you can see that the width, right, of the module in the rightmost column stays constant, right? So we are having to innovate to maintain that port density the same, right, basically, as we increase in speed more and more. So the question is now, what would happen after 400G? Most likely, if we don't go to onboard optics, the pluggable module will have to have a similar pitch, right, or size. So that's certainly one challenge. So this kind of puts it into perspective, the huge improvement in that bandwidth density that has gone on since the days of 10G, which is only, again, 15 years ago, if you think about it. Again, pluggabilities are still a requirement for optics. Non-pluggable optics have been around for quite a while. Actually, supercomputing have used it. Routers, multi-chassis applications within routers have used onboard optics, which are non-pluggable for quite a while. They have the benefit of having the optics very close to the ASIC. So you drive, the currents you drive are very low, so that brings down power dissipation per module and as a whole. So you can achieve very high densities from both thermal and physical standpoint. That higher bandwidth density can be achieved now by increasing the speed, increasing the number of optics, obviously. Today, state-of-the-art is one of these cubes, which are an inch by an inch, basically. They have 16 channels, 16 transmitters, 16 receivers in an inch by an inch. They're running at 25G per channel today. 50G is under development, again, mainly driven by supercomputers. And again, is that something that could be a play for networking? At 400G, we think the market has decided. So pluggable optics are certainly feasible and will be the predominant way to deploy optics. Again, QSFP, DD, OSFP. There might be some niche applications, obviously, that might require onboard optics. It's really at beyond 400G, 800, 1.6 terabit, where I think the industry is starting to look at onboard optics, and also co-packaging, right? Co-packaging ICs with optics much more seriously. And again, that's not a topic for this talk. So the optical technologies themselves, we mentioned them already. To go into more detail, right? Short reach VCSELs continue to be the most cost-effective way to deliver bandwidth under 100 meters, and that will continue to be the case for 400G, right? For various reasons, total cost is the primary one, if you take into account the cost of the optics themselves plus the fiber. So things like higher bandwidth in the VCSELs, we mentioned 50G and 100G PAM4, sparing capability, low RIN, silicon photonics, hopefully finally becoming mature enough to be deployed. So again, for intermediate reach, and then long reach, that's more traditional DML and EML, with again coherent optics coming a little bit closer into the data centers. So why multimode optics? Again, to make it clear, you hear a lot about silicon photonics in the market and so on, and we believe in silicon photonics for the right application, right? So if you look at anything under 100 meters, however, where you can use a directly modulated VCSEL, there is no question that from the thermal standpoint, power dissipation, number of components, types and complexity of the optical alignments and couplings, as you can see on the left-hand side, a VCSEL-based design is more cost-effective. It's simpler, easier to build, higher yield. An equivalent circuit using silicon photonics or design silicon photonics is shown on the right side. But again, more complex alignments, single mode, and so on. Things that you obviously can deal with if you have to, mainly for reach, but not if you don't have to. And again, under 100 meters, multi-mode optics using VCSELs, it's the most effective way. If we go, however, to the 500 meters to 2 kilometers, as we mentioned, we see silicon photonics beginning to shine. And this is a new application space. It's an application space that was developed for 100G networks around PSM4, 500 meters. PSM4 is a parallel optics, single mode parallel optics interface that was deployed early on in the days of 100G. It is now not being deployed so much anymore. It gave way to CWDM4 and other duplex single mode applications because they've come down in price basically. But it's an effective way of just using a single laser and then silicon photonics modulators to transmit, again, to 500 meters or 1 kilometer. So similarly to what PSM4 was at 100G, DR4 is being designed today. So the leading edge designs, right, that you see out there for DR4, 400G, are based on silicon photonics. They use a single laser, continuous wavelength, CW laser, that is then split and modulated independently into the 4 100G PAM4 channels. So again, the technology has improved, is improving for the right application. There's still yield issues, but they will be actually solved by the industry, we believe. It's really the right solution for that application space, given the high level of integration you can achieve. You can still not integrate the laser, right? You got to remember that silicon doesn't lay, so that won't change. So you can see a variety of interfaces will be deployed. The only purpose of this slide is to show that 400G would not be just point-to-point. It will be spread out, 4 by 100. It will be probably also connecting to 200G in some cases. So you can foresee a mesh of different interfaces and fan-out applications being deployed in different networks, in different deployment models. The industry is very active, actually. This is just some of the demos that the optical shows. There were many different vendors and even MSAs providing interoperability. So the industry is active, providing transceivers, bringing optics to market to support this deployment of 400G. So that's a good thing for all of us. If we look at now DCIs, right? I mentioned that already. Also at 100G, when you go into 80 kilometers at 100G or 100 kilometers, you have to use coherent technology today. We believe that also just like at 100G, applications up to 40 kilometers, maybe 35, can be best met using direct detect, like ER8, for example, which is being standardized. But it's really, if you want to go 80 kilometers or 100 kilometers, you're going to have to use coherent applications. We mentioned standardization. The OIF is standardizing a 400 CR interoperability agreement to really make sure that now coherent is interoperable, and that's something that does not exist at 100G, but it will exist at 400G. And then the Ethernet is now also standardizing a coherent interface in the newly created 802.3 CT task force, which is again focusing on an 80-kilometer implementation using coherent optics for 400G. So basically, the industry presumably will move away from the current model, which is using transponder boxes, and you may recognize some of these. Some of them might actually be tonight in the beer and gear. So a lot of very healthy ecosystem for transponder, 1RU boxes for DCI with 100G ports, using things like CFP2 ACO, analog coherent optics, and so on. That's being deployed today. That's mature technology being deployed by many networks around the world. What we're talking about here is improving, again, coherent technology, improving the DSP, lowering the size, the power of the optics, the optical packaging, to fit in a QSFP DD, right? What you can foresee is in 3 years, right? In 4 years, there will be QSFP DD modules, very high density transceivers with coherent technology, the DSP inside, DCO, that could be plugged into any switch, right? That's the ultimate goal. In a truly interoperable environment, again, given all the interoperability agreements and standards that are being defined. So my last slide, what happens after 400G? Again, not a topic for this talk. I think you're going to hear Andy talk about it tomorrow afternoon in his talk, more in detail. But if we see a different deployment model now moving into doubling again the speed, requiring 800 gigabit Ethernet, the question is really, is pluggable feasible or not? That's what matters for some of us in the physical layer of the device, subsystem industry. Is it pluggable or not? Is it feasible or not to make it pluggable? Some are thinking OSFP could be the right form factor, maybe not. If it's not feasible, then the whole market and the industry dynamics, both technically and also from the business model standpoint, will change by having non-pluggable optics for many of us. And if it is, of course, how do you implement it? Thermal requirements, what does the electrical interface look like, and so on. And there's work going in that direction as well already. The IEEE is now defining a 100G PAM4 electrical interface in the new task force 802.3 CK. Right? So this is actually a single electrical lane running at 100G Ethernet now using PAM4 modulation. All right, so that was it. Thank you so much. I think we have a few minutes for questions, not too many. Sorry.
Alan Hannon, CrowdStrike. Good talk. You said several times in your presentation that they'd be here in a couple of years. Do you promise?
Which one?
All of them.
All of them, of course.
Okay.
Yes, some of us are more aggressive than others in the industry. What we need to remember is that optics are harder to predict than some of the other, digital electronic design. There's a lot of innovation needs to happen in optics, and optics tend not to follow Moore's law so adequately. All right. Thank you so much. Appreciate it.